Welcome back. This is the second video in the work application. In the last video, we went through problems 1, 2, and 3, and now I'm going to do 4, 5, and 6. You'll see that there are slight differences from the previous problems, but I will try to pinpoint why those differences exist. So in number 4 here, we have a 100-foot cable weighing 200 pounds is hung from a skyscraper. How much work is needed to raise the cable to the top of the building? So in this case, I've got a quick sketch of a tall building here and a visual of the blue rope hanging from the top. I'm viewing the top as point 0 with the positive axis downwards. And then I am breaking this rope up into very small intervals of size delta x. And then I'm imagining that there is essentially a distance x that puts us within that small interval, and that everything within that interval is coming up essentially at the same rate, same mass. And so that interval is treated like a small object that we are lifting up. And so it's really important to understand these details as I progress. Now I'm going to focus and view that since I know the cable is 100 feet long and weighs 200 pounds, that means that there are 200 pounds per 100 feet of cable, or we could view this as 2 pounds per foot. And with being in a small subinterval, and that subinterval is of some distance or measure, that means that the force is going to be 2 times some x. And so you'll notice that the units match up. We could check this, and so the units are pounds per foot, and then the x is in feet. And so we are left with pounds. And remember, in the last video, I mentioned that for this course, pounds is viewed as a force. So we have our force function. Now we want to figure out the work required. And so the work is the integral of our f, which is 2x dx. And we are integrating going from 0 to 100. Remember, we're picking up the piece right at the top, which is our point 0, and pulling everything even down to the bottom length. And remember, the cable is of length 100. And so this is what's going to give us our answer. It integrates to x squared, which we evaluate from 0 to 100, which gives us 10,000 foot-pounds. And recall that looking at the relationship of units, if we want 10,000 foot-pounds in terms of joules, then we would need, we know that there's 1 foot-pound per 1.36 joules. So 10,000 foot-pounds is 10,000 times 1.36. Which is going to give us let's see, we're going to move it over 10, 20, 10, 100, 1,000, 10,000. So 13,600 joules. And so what changed here is instead of lifting up a single object, we lifted up a long, sizable object, and that we had to break up into small pieces. So now let's take a look at problem 5. We have a 10-meter tall inverted circular cone tank with a radius of 4 meters that holds 8 meters of water. Find the work required to empty the tank by pumping all of the water to the top of the tank. And we are given that the density of water is 1,000 kilograms per cubic meter. I've created a sketch here of the tank. So it's an upside down cone. You've got water that's not full in it. It just goes 8 meters up. The cone itself is 10 meters tall, and I've got that dimension on the right side. The radius is 4 meters on top. And again, in this case, I'm choosing to essentially put my origin at the top of this cone with the positive direction downwards. And so that means that the water starts at 2 meters below, which is the positive direction, below the top, and goes all the way down to 10 meters. So when we integrate, we're going to integrate from 2 to 10. The closest bit of water needs to go up 2 meters, and the furthest needs to be pumped up 10 meters. So I need to figure out the force equation, essentially, for this first. And I'm going to, again, break the object, which is this water, into slivers. In this case, the shape of the slivers, unlike the rope, which was a small length, here it's going to be a tiny cylindrical volume. And I've got that in green that I kind of sketched there, of thickness delta x, and of some radius r. So there is some radius r that we don't know, but we'll work to try to figure that out. Okay, so what is that radius? Well, we have our big triangle. Looks something like this. We know there's 4 meters for the radius, and the height is 10. But then within this, somewhere in general, we have for the small bit of volume of water that we want to bring up, we have it having radius r, and we need to know its height. Recall that we're putting the origin at the top, and so that means that our x is going down to where the radius begins, which means that this piece, because the total height is 10, this is 10 minus x. So using properties of similar triangles, we have that 4 over 10 equals r over 10 minus x. So this is ratio radius over the height equals radius of a smaller triangle over its height. And solving for the radius, we get 4/10 times 10 minus x, which simplifies a little bit to 2/5 times 10 minus x. So that's the radius. Now, why do we need that? We need that because now I need to know what is the mass of this object. And mass is going to be density times volume. And we are given density of 1,000 kilograms per cubic meter. And I'll just use V for volume for now. So I need to know, well, what is the volume? And the volume of that small cylindrical sliver That is given by, let's do that over here. So that volume is pi r squared h. This is the volume of the cylinder. And so our h is the delta x. And our r, we had just found to be 2/5 10 minus x. So that's going to be 4/25 10 minus x squared. And here's our volume, which I am going to sub in. And that is going to give us, let's see, 160 pi times 10 minus x squared. So let me just check that. So we've got 1,000 times 4 divided by 25, which is 160. So this is our volume. Or sorry, the 160 pi times 10 minus x quantity squared is our mass. We know that in order to pump or push the water up, that's going to have to battle gravity. So we have that F equals mg, where m is what we just found, and g is 9.8 meters per second squared. So when you multiply through, this is going to give us 1,568 pi times 10 minus x squared. And there's a delta x. And now we need to integrate. So work is going to be the integral again from 2 to 10 of 1,568 pi 10 minus x squared, and the delta x becomes dx. And when you integrate this, you get a very large number, which is around 1,70,421.333 pi. And this is in joules. So you could either expand that polynomial and integrate, or you could use substitution. Either approach is fine, but you should be able to confirm that this is the answer you would get. Which brings us to our last example, and this is the force in newtons between two charges is given by this f of x function, where Q1, Q2 are electric charges in coulombs. K is 9 times 10 to the 9th as a constant, and x is the distance in meters between the charges. We want to know how much work is done to separate two electrons from 1 picometer to 4 picometers. So we're given the force function in this example, which means we are going to use that. So K is 9 times 10 to the 9th. Electrons have a charge of 1.6 times 10 to the negative 19. And that's the same for Q1 and Q2, so I'm just going to square that. And we want to integrate this with respect to meters, and so 1 picometer is 1 times 10 to the negative 12. And 4 picometers is 4 times 10 to the negative 12. So when you integrate this, which you could convert the 1 over x squared to an x to the negative 2 and integrate, and I trust that you can do that on your own, but what you should get is about 1.728 times 10 to the negative 16th joules. So again, for 5 and 6, I did most of the work for you as I led you through this. I trust that you can do the integration on the side, but at least I set it up and you have the answers that you should be able to get. And that is it for work. So the challenge is to deduce whether you are considering a point mass, like we're looking at for problems 1 and 3 in the last video. Problems 2 and 6 gave you force functions, which you could use directly. And problems 4 and 5, you essentially had large objects that you had to break into pieces, create a force function, and then integrate that. So there's different scenarios that you could come across, and these examples cover them all.